Welcome to this explainer on the mechanics of motion. Have you ever watched a self-driving car gracefully navigate a busy intersection and wondered how it actually works? How does a machine of that size mathematically calculate exactly where it needs to be? And more importantly, how does it safely and physically get there without crashing? Well, today we're going to break down the foundational physics that make those modern marvels entirely possible: kinematics and dynamics.
Here's our roadmap for today. First, motion, how versus why. Second, kinematics, the study of motion. Third, dynamics, the forces at play. Fourth, real-world engineering applications. And finally, number 5, mastering the mechanics. Let's jump right in.
Section 1, motion, how versus why. Okay, let's dive into this. To build a conceptual framework, I want you to think of a video game. First, we have kinematics, which is essentially the how. Think of this as the pure mathematical code dictating exactly where a character moves in the game world, completely ignoring any outside physical forces. Then, on the other side, we have dynamics, which is the why. Dynamics acts as the physics engine. It introduces simulated gravity, the weight of objects, collisions, and actual physical effort into the whole equation.
Section 2, kinematics, the study of motion.
So our starting geometric baseline here is displacement. We are stripping away gravity, we're stripping away friction, and we're looking purely at the shortest straight line distance between an initial and a final position. Because, before we can track speed, we absolutely must establish exactly where a journey starts and ends. Now layer on time, and boom, you get velocity. It tells us not just that an object moved from point A to point B, but exactly how swiftly it made that trip. And if you track how that velocity changes as the clock ticks on, well, then you have acceleration. Whether it's speeding up or slowing down, acceleration really completes our fundamental picture of the how. Now, what's really interesting about this slide is how we can translate these definitions into a practical engineering scenario, completely skipping the scary math. Let's say a car starts from rest, meaning, of course, its initial velocity is 0. And it accelerates uniformly at 3 meters per second squared for exactly 5 seconds. Just using our basic kinematic toolkit, we can predict exactly how fast that car is going to be going. And the result is 15 meters per second. By simply taking that acceleration of 3 and multiplying it by the 5 seconds, we get our final velocity. Punchline: this beautifully demonstrates how kinematic equations can perfectly predict real-world motion using nothing but distance, rate, and time. It's like a giant puzzle coming together. Section 3, dynamics, the forces at play. Because in the real world, a car doesn't just magically accelerate. An engine actually has to burn fuel and work against the car's physical weight. You literally cannot talk about dynamics without bringing up Sir Isaac Newton. You likely already know these laws by heart, but engineers, they view them as absolute non-negotiable constraints. Inertia, force equals mass times acceleration, and action-reaction. These are the absolute bedrock rules for designing any physical system. And from that bedrock, engineers expand into advanced dynamics. We're talking the work-energy theorem, impulse momentum, and the conservation of mechanical energy. This is the heavy-lifting math that evaluates massive energy transformations. It's how we ensure a car safely crumples in a crash test, or how we calculate those thrilling yet perfectly safe G-forces you survive on a roller coaster.
Section 4, real-world engineering applications.
So let's see pure kinematics in action first. Engineers use these exact motion calculations to optimize car suspension paths, which is what keeps your ride perfectly smooth when you hit a pothole. In manufacturing, it's what ensures conveyor belts and gears run flawlessly for totally efficient power transmission. And this brilliantly illustrates one of the most fascinating applications out there: inverse kinematics in robotics. Imagine a robotic arm working on a fast-paced assembly line. Step 1, the system identifies the desired target coordinate in a 3D space, in X, Y, and Z location. Step 2, it computes the exact required joint angles needed for the arm to reach that spot. And step 3, it executes the precise movement. The robot is mathematically calculating the perfect grip and path before it ever moves a single mechanical muscle. No guesswork, just precision. But while kinematics plots the path, dynamics is what ensures the structure actually survives the trip. Aerospace engineers use it to balance intense aerodynamic forces. Civil engineers rely on dynamic calculations to evaluate oscillation frequencies, making absolutely sure a bridge doesn't hit resonance and literally tear itself apart during a massive windstorm. Section 5, Mastering the mechanics.
Now, if you're looking to move beyond the theory, the source material highlights several awesome tools. Textbooks by Merriam or Thornton are fantastic for your foundations. Digitally speaking, Khan Academy and MIT OpenCourseWare offer really great free lectures. And if you want to model complex systems yourself, MATLAB and Simulink are pretty much your industry standards.
But having the resources is kind of just the starting line, right? You need the right techniques. Active note-taking, like actually summarizing concepts in your own words, is vital. So is practicing multi-step problems and using group study to uncover your own blind spots. But above all, drawing visual diagrams of motion is essential. Visualizing scenarios like actually sketching out the parabolic motion of a projectile before you ever write down an equation is the ultimate key to unlocking true understanding. So the crucial point is perfectly summarized right here in this quote from the text. Understanding these concepts enables predictions of how objects will move or interact, providing a comprehensive framework for analyzing physical systems. Mastering these two branches means you aren't just memorizing formulas on a chalkboard, you are literally understanding the operational rules of the universe. From the suspension in your car to the robotic arms building our future, kinematics and dynamics are the invisible hands guiding our physical reality. Now that you understand the mathematical code and the physical engine driving it all, what invisible forces will you engineer next? Thanks for joining me for this explainer, and keep learning.